Hello and welcome. You ever stop and think about the actual shape of things? Not just big things, but the molecules that make up everything. Why is one V-shaped and another a straight line? Well, it's not random at all. It all comes down to how atoms, especially our good friend carbon, decide to arrange their bonds. Today, we're going to pull back the curtain on the concept that explains it all, orbital hybridization.
Okay, let's just jump right into the big mystery. We all know carbon is famous for forming 4 bonds. But here's the catch. If you look at a carbon atom's standard toolkit of electron orbitals, they're not all the same shape or energy. So how in the world does it make 4 bonds that are perfectly identical? Like the ones in methane? I mean, that shouldn't be possible, right? This is the exact puzzle that we are going to solve.
So here's our game plan. We're going to start by really digging into that bonding puzzle. Then we'll figure out what hybridization even is, and after that, we'll break down the 3 big types for carbon, sp3, sp2, and sp, and see how each one cooks up a completely unique and totally predictable shape.
All right, let's get to the heart of it. Why do we even need this new idea of hybridization? Well, because the simple, out-of-the-box model of atomic orbitals just doesn't match up with what we see in the real world.
Think of a carbon atom's orbitals like a set of tools. It has one spherical s orbital and 3 dumbbell-shaped p orbitals. They look different and they have different energy levels. So common sense would tell you that if you built something with these different tools, you should get different-looking results, right? You'd expect some bonds to be different from the others. But then you look at a real-life molecule like methane, and that's not what's going on at all. All the evidence shows that the 4 bonds in methane are perfect clones of each other. Same length, same strength, everything. This is a flat-out contradiction. The simple theory just breaks. Clearly something else is going on inside that carbon atom before it even makes a bond. We need a better explanation. And that better explanation, that new idea, is called hybridization. It's a really elegant concept that perfectly solves the mystery of how carbon makes these identical bonds and creates all the specific 3D shapes we see. So what is it exactly? Well, simply put, hybridization is when an atom's own orbitals mix themselves together. But why? It's all about energy. By mixing its orbitals, the atom can form stronger, more stable bonds. It's like it's reorganizing its toolbox to build a better, sturdier structure. It takes its original different orbitals and creates a brand new set of identical ones to work with. Now, don't let the word scare you off. The core idea is incredibly simple. Hybridization just means mixture. It's like when you mix salt and water. You don't have separate salt particles and water molecules anymore. You have a totally new thing, salt water. It's the exact same principle for orbitals. They mix to become something entirely new and uniform.
Okay, let's look at our first and probably most common type of hybridization, sp3. This is carbon's go-to recipe for making single bonds, and it's the key to finally understanding our friend, methane.
And what's cool is the name itself, sp3, tells you the exact recipe. It's made from 1 s orbital and 3 p orbitals. So if you do the math, each of these new hybrid orbitals is 25% s and 75% p. The name is literally the formula. So how does this happen? It's basically a 3-step process. First, carbon just hangs out in its normal ground state. But to get ready to make 4 bonds, it gets a little boost of energy and enters an excited state. An electron jumps up to an empty slot. Now it has 4 electrons all ready for action. And then the magic happens. In the hybridized state, that 1 s orbital and those 3 p orbitals all blend together. And poof, you get 4 brand new, perfectly identical sp3 hybrid orbitals. And there you have it. Our methane puzzle is solved. You have 4 identical orbitals, and they all have negative charges, so they want to get as far away from each other as possible. The shape they naturally form is a tetrahedron, with that classic bond angle of 109.5 degrees. This is the shape of methane. So the big takeaway is this. sp3 hybridization leads to a tetrahedral shape. It's the signature of single bonds. Okay, let's move on to the next case, sp2 hybridization. We're about to see how a different recipe builds a totally different kind of structure. This is what carbon does when it needs to form a double bond. And just like before, the name is the recipe. For sp2, we're mixing 1 s orbital with just 2 of the p orbitals. That means our new hybrids are about 33% s and 67% p. But wait a second, carbon has 3 p orbitals. What happened to that last one? This is where it gets really interesting. That third p orbital just gets left out of the mix. It stays as it is, unhybridized. So an sp2 carbon atom basically has 2 kinds of tools now.
It has the 3 new sp² orbitals that form the strong foundational skeleton of the molecule. We call those strong bonds sigma bonds. And then there's that leftover p orbital, which forms a weaker side-by-side bond called a pi bond. And guess what 1 sigma bond plus 1 pi bond makes? A double bond.
So what's the end result? Those 3 sp² orbitals spread out as far as they can, forming a flat triangle. We call this shape trigonal planar, and the bond angles are a perfect 120 degrees. You see this in molecules with double bonds, like ethene. The leftover p orbitals then line up to form that second part of the double bond, sitting above and below the flat triangle.
And that brings us to our last and, honestly, our simplest form, sp hybridization. And I bet you can guess what this recipe is for. It's for when carbon needs to form a triple bond.
The recipe for spec couldn't be simpler. It's a straight 50-50 mix. One s orbital combines with just one p orbital. This means there are now 2 p orbitals left over, unhybridized and ready to get involved.
Now think about it. If you only have 2 hybrid orbitals, what's the farthest they can get from each other? They just point in opposite directions. This creates a perfectly straight, linear molecule with a bond angle of 180 degrees. The 2 leftover p orbitals then form 2 pi bonds, and you add that to the main sigma bond, you get a triple bond, just like we see in ethane.
And here it is, the whole concept in one simple table. This is your ultimate cheat sheet. You can see the clear, predictable pattern. Single bonds mean sp³ hybridization and a tetrahedral shape. Double bonds mean sp² and a trigonal planar shape, and triple bonds mean sp and a linear shape. It's this beautifully logical system that really is the architecture of chemistry.
So why does any of this really matter? Because, for a molecule, its shape is its destiny. Seriously. The shape dictates pretty much everything. How it will react, if it's polar, how it will interact with other molecules, even its biological function. So by understanding hybridization, we're not just drawing some abstract shapes on a page. We're actually unlocking the ability to predict how the fundamental building blocks of our universe are going to behave. And that, well, that's an incredibly powerful